Hello, let's talk about the CCG4 Eval kit. Some of the features I'm talking about won't be included in the data sheet or be quite hidden, so let's talk about it. We've got a daughter card and two base boards. Now this daughter card has a main processor. It's controlling the two USB ports on both sides, here and here. And these two base boards are exactly the same. They're exactly the same schematic, exactly the same PCB, just rotated. So this is DisplayPort, USB 3, USB-B, micro USB, the debug connector. Now here we have a buck connector. So on these pins, there's going to be between 15 to 20 volts. So let's talk about the case where you've plugged in a DC jack. Yeah, so here you've plugged in a DC jack, and they're assuming 24 volts. 24 volts goes into here. It inputs to both of these devices, and that means both of this is both a power provider model. So both of these are power providers. There is no capability of power sinking here. And whatever the output on the Type-C header, it will be outputted here. So the device requests 5 volts, there will be 5 volts here. The device requests 20 volts, 20 volts will appear here, and the same for here. Power output. And if we go down, we look at the USB-C case, where this requests either 5 to 20 volts, 15 to 20 volts. It has to request a high voltage. 15 to 20 volts. Now the 15 to 20 volts appears here, the same that appears here. Now at the output header there won't be anything, absolutely nothing. I mean, if you flip this around and you put the Type-C in here, and you also request 15 to 20 volts. The 15 to 20 volts appears on the power output header. And let me check something. Yeah, the 15 to 20 volts appears on the power output header. Sorry, I made a mistake. So I made a mistake there. The 15 to 20 volts appears on the power output header. Nothing appears on the power input header. Same way as here, 15 to 20 volts appears on the power output. Nothing appears on the power input. And the power input is unpopulated on J12. And that whole sheet in the schematic for the power input, which is this sheet on J12, which is J12, nothing will be here. If you've got a USB-C as your power adapter, in that sheet, the power input header will be empty. So here it assumes either USB-C in, which is providing 15 to 20 volts, such as this example here, 15 to 20 volts, providing 15 to 20 volts. So that's USB-C in on the other board. This board does not support USB-C power adapter in, power adapter in. It doesn't support it, and it will break a few things if you do that, because the power out is going straight into the power in, and this sheet is not used. And if you do, you're going to be powering up. You're going to try and send 5 volts down this pin, which is not supported. So there needs to be some logic here. There needs to be some logic between the power out and power in, so that if there is something on the power out and something on the power out, don't do anything. If there's only one of the power outs is on, send the connection. If they're both on, don't send the connection, and that should work. It won't do anything. They'll just be both power sinks, and nothing will happen. So that extra logic is required. And if we talk about the USB-C implementation, power provided in, and they say 14 to 20 volts here. Okay. And then at 14 to 20 volts, should appear there. I think the multimeter reading is wrong. It should get 40 to 20 volts because that's the power out. Goes straight into the other side, which is powering the device. That other device says it needs a minimum of 14 volts, so I think this is a bit wrong. I think this multimeter reading out. You got to assume this is 40 to 20 volts, and here you get 40 to 20 volts, which then powers up this side of the circuitry, and the USB port will only request 5 volts, so that's okay. There are a few issues with this board. This USB provider circuit can only provide fixed voltages. It only can provide 5, 9, 15, and 20. It doesn't support PPS, doesn't support any voltage outside this range. And the way they're doing this is by putting a 2-wire decoder, so either a 00010, 1101, and based on that you get 4 outputs. And depending on what you choose here, we will 0, 1, 2, 3, 4, and depending on what you choose, you'll get a different voltage divider circuit on your feedback loop. For example, you get 5.49 on the feedback loop, and the positive side of the feedback loop is always the same. And it's always either 20, 16.9K, and the rest of them is decided by this switch. Technically, you could choose another one and do that way, but it's kind of a hack. This is, and you'd have to change the software ideally. But this is only powered up. This circuit field is only powered up. This decoder circuit's only powered up when the device is externally powered in provider mode. Because when you've got voltage here, there's voltage here, there's voltage here. So this circuit powers up when there's voltage here, and when there's voltage here, there's voltage here. It's more ideal to use the I2C buck booster from the motorbike charger, which uses the car charger, which uses CCG4 and the ACT5101. And this is a buck booster, and uses the I2C lines to tell the output voltage what it can be, and this allows you to get a huge range on output voltage. So if you look at this, it's incredible what you can get out of this chip, and it should give you the full 5 amps. Well, they haven't implemented it here. You should get the full 5 amps. So you get wide input, supports wide output, so this will meet the USB-C standard, and it all can output about 5 amps. They've implemented the 3 amp version here. So VL is limited here, DevKit can support it, probably a software adjustment. And we've got a switching at 500 kHz, and the software for this can be found on their website. Fortunately, the dev board for this can't be found on their website. Frustrating. Alright. So we've got this. So this is the baseboard. The baseboard means the backboard, and the daughter board is the processor board. So this is the backboard. And there's a lot of repetitions on this backboard. Anyway, this is the power page. We select the output voltage. So we got. And then this board is this page is converting the power that you get from either USB P power, which is provider. P means provider. There's a provider power, or consumer power. Consumer power appears on the USB-C line. There you go. So you request this power from another device. You're a UFP, and you requested it here, Type C, and USB-C power. Well, it says Type C power. This is power here, and if you go to the daughter board, you look at the power provider setup. USB-C power is from the consumer path, and USB-C power is sent to the Type-C USB through this FET. So this FET, depending on these and the consumer path, so if both of these are off, it'll be in consumer path, which turns on these FETs, turns off this FET, and then you got the Type-C V bus. So technically this is not really used because either of these, when either of these have power, this will have the same voltage as either of these two, because they're both going to the FET. And USB-P power here, USB-P power is in, this FET turns on when you turn on these one and one, and you get the voltage of the Type-C bus, which then goes to this connector here, Type-C. Alright, so you got either power, so either's powered up, and this page doesn't care whether you've got something populated here or you're syncing power from the Type-C port. And either one of those, and you got a buck converter. And also this page assumes that you don't have power on both sides. So there's an assumption here. Assumes that you don't have power, so only one of them is on at the same time. On at once. And you get 3 volts and you get 5 volts out of here. And then this V out, of course, comes from this. That means that this is assumed that this is power. So this is when we're providing power. There's a voltage divider between here and here. And it's looking at the feedback voltage. And it says the feedback voltage should be 1.25. They've given you a 9% margin. So less than 9% and greater than 9%. And if it's so normally normal proportion, this is 1.25. 1.25 volts is op amp is off, comparator is off. So when it's off, the end tray is off, which means the V out goes to power good. Everything's happy. In a converse case, when the VF is greater than 1.35, this is on, which sends voltage to the gate, turns on the gate, shorts out this line, which turns off power good. And the same principles for the other side. They've done a nice voltage divider there. Alright. And they got an on LED, that means both converters are working and this board is powered up. And yeah, so Type-C V bus. This goes to the daughter board, which goes to on the debug connector. It goes to here, one of these pins, the daughter board. There you go. Type-C V bus. So whether you're a provider or consumer, you get Type-C V bus and USB-P power, USB-C power. So all three on these. So whether you're Type-C power, USB-C underscore power, which means your consumer. So what happens is this goes to here, goes through these FETs, and it becomes USB-C power. And then this appears right on the J7, and J7 is here, which is also the power output. So our power output is connected to the consumer path directly. Yeah, so if we're properly consuming power, it's not outputting the voltage on the V bus. It's only outputting the voltage if assuming you are consumer power. So the voltage only is here present if you're on the consumer path. Otherwise, there shouldn't be anything. And then this would always have voltage whether you're producer or consumer. And this is voltage on here if you are a producer. And when the FET turns on as a producer, the voltage appears on here as well. No, yeah, output appears on here. All right, so let's talk about this power board, power circuitry. So we've got USB provider power provided from the first circuit board on this page. Provider power, assuming you got DC in, or the other board's powering you. And then go back-to-back FETs to prevent current from. So if there's voltage on here, it doesn't flow back to the provider page. And it only allows voltage one way. When this FET is off, voltage can't flow. The current can't flow. Can only flow when this is on. Alright, so we got the power, got a 10 milliamp resistor to a current sense circuit, current sense IC. This current sense IC outputs current relative to here, and then to convert that current to voltage, you multiply that current, the output current, by this 10k resistor, and give you the voltage. So here we have 2.14 volts at 5.35 amps. That's what they've set this gain to be. And it goes into here, and you've got a comparator also at 2.14, and the voltage increases as the current increases. So in normal operation, and let's say 2 volts in here, the comparator's off, comparator's on, because it's greater than this. Comparator's on, output is on. It's a push-pull device. So you've got, let's say 5 volts on here, plus or minus a little bit. Just a little bit. So that means this FET is on. So you've got a final FET which connects this point through this FET, through this FET, through this FET, through this FET. So these are all AND gates, and it turns this one on. So this specific FET is disabled when there's overcurrent. So when there's overcurrent, this output is low, turns off this FET. So this is the final FET and prevents this one from turning on. So, and this is only overcurrent for the provider path. There's no overcurrent. There's no current detection for the consumer path. It's only done on the provider side. And there's a zero link if you do put it in, you've disabled overcurrent. Now this FET is pulled to this point. And here you got a OCP. So when the output is on, or normal operation, which is all good. When the output is low, the IC knows that it's tripped because of overcurrent. Alright. Now, default case, so there's two controlling signals here, VBus C consumer control, VBus P provider control. So these two pins are used to control whether your consumer provider. So in the case where they're both 0, let's say you've started up, and you decide to be both 0, the consumer path is on. And this makes sense because the consumer path goes to here, goes to this FET. And so this is 0. Alright, so this FET is off. That's fine, not a problem. And it goes into here, goes into here, goes into here, and turns off this FET. So we know we're not going to be in provider path because this is off. And similarly, if VBus provider is on, is 0, this FET is off, and so is this FET. So both of them are off, both of these two are off. It's kind of like double protection. Yeah, so if both of this is off, what does this FET do? Now this FET, and let's not talk about this FET, let's talk about these resistors. So by default, the consumer path is on. Because the voltage here, you got, let's say 20 volts available to you. So you get 20 volts here. And this charges up slowly, this capacitor charges up slowly, not a problem. And we have this voltage divider, right? And by default, this FET is off. So let's assume this FET doesn't exist. And we've got this voltage, so this resistor pulling this gate to ground, right? Assuming this doesn't exist. When we pull the gate to ground, we get power here, and 20 volts here, and 20 volts on this pin. Now when we have 20 volts on this pin, 20 volts is pulled up to the gate. This is a PFET, so this turns off this gate. And it goes to here, we know both of these two are off, because these two are off. And this IC is when there's over voltage. This is on the voltage divider. Voltage provided from there's a signal provided from the CCG4 chip. So assuming that you're not tripped, this pin is off. So this bit does not connect to ground, right? So by default, this guy is pulled to ground. Consumer passes out to flow to the Type-C V bus. That's fine. Now, if any of these cases happen, and this is because of these resistors. Now, how do you turn off these resistors to tell it you don't want to be consumer path? And you do that by turning on either one of these two on. When you turn on VC control, this turns on this FET, which pulls this gate to. So it connects this bit to ground. So it pulls this bit to ground. Yeah. When we pull this bit to ground, this turns on this FET. And when this FET is on, it shorts out this point to. So it shorts out this resistor here. And this resistor was acting as a voltage divider from the 20 volts to this point. So it was actually helping pulling the gate low. When you're shorting this out, you've disabled the 100K, and you've got 20 volts here, 20 volts here. So the gate just pulls up high. So the voltage at the gate here will be 20 volts because you've shorted out this resistor, and you've got 20 volts here. There is a 10K resistor to ground, but you'll still get 20 volts here. So when this is off, but when this circuitry is off, you've got 20 volts divided by 10K QS in current, at least, minus all the other bits and bobs that are kicking around in this circuit board. And this isn't the most power optimal design. Right, so this is how they're turning off. And when you turn on this one, this pulls the gate low, shorts this bit out, sends 20 volts onto this pin, which turns off the gate. When you turn both of these are on, these two are on, that's fine. We know this consumer path is going to be off. And this turns on this FET, also turns on this FET. This FET is pulled up high by this unless there's an over voltage trip. There's a lot of logic here, and you've got V-bus discharge, and this shorts out the ground to a resistor. There's a lot going on here. They've tried their best to prevent the consumer and provider path being on at the same time by adding an extra signal. And then they've also allowed for an off condition for both. This exact same circuit is provided on the other side for the other ports. So these two circuits are actually on the CPU board, and one for each side. So one for each port. So there's port 1 and port 2. This is for deciding whether you want DisplayPort or USB, high-speed USB on both ports, and that's fine. So if you're not using DisplayPort, you don't need this sheet. You'll need these two sheets, one for each device. We've got this CCG4 IC, and these are the ports interface, which you'll see here. And this connects to the daughter board. This pin here. On this, you'll get the And the pinout is exactly the same for both, but just flipped because you're going to get the connector rotated. You're going to get the connector rotated because the orientation of this board is at J12, and then it's rotated to J12 here. Alright, so we've got P control, C control, and this charge pin, each port, which we've seen here. Oh no, we've seen here, P control, C control, and this charge pin. These are available on the connector. I'm not sure why they're not used on this sheet. So if you look, it could be used for debug because it goes through the debug, P control, C control. So I think that's the only place it is used. If we go to P bus P control, I don't think it's used on this sheet other than debug. Yeah, right. So it's only for debug. Sent to the other connector. Serial muxes. Just select serial line you want to use. This is also for debug the DisplayPort line. Oh, sorry, ignore that. We've got VBus monitor. This is all quite interesting. This VBus monitor. Now this VBus monitor comes on. I think it comes from the feedback line, the regulation feedback. I remember seeing over here. Alright. Oh, okay. Trees, interesting. Doesn't go anywhere. Right. So pin 26. Yeah. Alright, fine. Doesn't go anywhere. There is a voltage monitor which I'm interested in. So there used to be a while ago. There used to be the power goods connector on this pin. So it would see if your P power was regulating well. So a voltage divider going into the CCG. But they've changed that to, and it's actually the same net. Reuse that net, and they put it here, power good. They've decided that it's better to look at whether the device is in with regulation, the feedback voltage is correct when you're providing power, rather than looking at the actual voltage. So they've moved it to the other sheet. So this is disconnected, power good. I thought that was quite interesting. And it goes to here, power good. You got the over voltage strip we've seen. Here, over voltage strip. And we'll of course see the overcurrent strip somewhere else. Anyways, we've got the CC1s and CC2s. These are on the USB-C connector on both boards. CC1 and CC2. And so this IC is kind of mirrored. You see the same thing on both sides. I think that's about it. Not much left to talk about on this page. Beacon power switch. This is a FET, so it sends 5 volts. If the 5 volts is on, it sends 5 volts. So this tells you that the 5 volts is working. So the controllers are all working. So the 5 volts here, V0 underscore P. That means we've got 5 volts coming in. That means that regulator on this sheet is working. Because interestingly, this 5 volts goes to the connector here. There you go. So both you got to get both 3 and 5 volts, which is used to select which one it connects to, and the checking. Now that's all good. Yeah. There's a V-bus monitoring circuit. So where is that? There. So they got the voltage divider on the V Type C. This is the output Type C V-bus, which is here. They've got a voltage monitoring circuit here, which makes more sense. So previously they had voltage monitoring only on this bit, but it makes sense to voltage this bit and keep this one in regulation. Because you've only got fixed voltages. You got 9, 5, 12, 15, something like that. So yeah, this is Type C, and you do the same thing for both. There's both monitors. You've got the prog monitor. Can't remember what it's called. The easy prog monitor, something like that. Check what it's called. Mini prog 3 programmer. And you got supply select, either 3 or 5. I think that depends on what voltage level you want to talk to it. And whether you want the I/O voltage to be the same. And it doesn't make sense to have the supply select of 5 and the I/O 3.3. I think that's quite confusing. I think there needs to be more investigation there. What else have we got on here? We'll talk to this bit, 3 to 5, and monitor that we're in regulation. So this is switching whether you want USB 3 or DisplayPort, either one of those two. Transmit lines, receive lines. So if you're not using the USB 3, you're only using this for power delivery, you wouldn't need this circuitry here. USB is for serial, this is for programming. It also provides I2C. This chip provides both UART and I2C, both on the same chip. Debug connector and the bus connector. What's interesting is if you were going to use this for a dual port controller, dual USB-C port, and you're going to lay out this board with the daughter board and elements on both boards, you'd be repeating yourself because the base board, imagine you've got 2 of these. You've got 2 USB to serials, both of them. You will need that. You got 2 regulators. You have 2 3.3 volt regulators, so you could eliminate one of those 2, which will eliminate this circuitry here because you've got 3 volt 3, and you don't have 2 sources of 3 volt 3. So you can eliminate this circuitry by having only one of these boards. You don't need USB power providing monitoring. That makes sense to do that because you've got 2 providers. It makes sense to keep this circuitry. I would probably change that to an I2C one. It means you have more greater variety of voltages. Obviously, you need some software for that. Yeah, that's an overview of the CCG4 and the schematics behind it.